Hey there, I'm Nix, and the topic of today's video is solving the diagonal traverse problem on the LeetCode website. As always, solving this problem in the C++ language and giving you a detailed explanation of the entire process, through the planning of the algorithm, to the coding of it, to the time and space complexity analysis of the algorithm, as well as looking at LeetCode rankings. If that sounds interesting to you, then stay tuned. Welcome back. Let's get to it. So we're given an m by n matrix, mat, and we want to return an array of all of the elements of the array in a diagonal order. And we're given a picture here and some examples to look at, as well as some constraints down here. So essentially what we want to do is walk the path along the matrix in this specific way. And all of the values that we come across as we walk that path, we want to put into a vector. And at the end of walking that path, this vector will record all of the values that are present in the matrix, ordered according to this diagonal path that we walked. So now looking at constraints here, one thing to note is that m and n could potentially be equal to 1. And if that's the case, then the vector of vectors here that we're going to be given, well, a diagonal path for that is going to break down in that situation when m or n is equal to 1. Because in that case, we either have a situation where our outer vector only houses one inner vector, and that inner vector contains all of the values that we want, or our outer vector contains many inner vectors, but each of those inner vectors only contain one value. And in either case, there really isn't a diagonal path to walk in order to get those values. So because of that breakdown, that's an edge case that we need to take into account. But now, how do we actually walk this diagonal path in code? Let's look at this example a little closer. We have a vector of vectors that essentially has 3 inner vectors here. And of course, whenever you want to access something in a 2-dimensional vector, you access it according to mat I, and then another bracket here, mat I, j. So you want to tell it which of the inner vectors you want to access, and which specific value in that specific vector do you want. So looking at this picture here, 1, 2, 3, 4, 5, 6, and 7, 8, 9 are all of the values that are present in 3 vectors. So each of these vectors correspond to essentially I. If I is 0, you want the first vector. If I is 1, you want the second, and so on and so forth. And as it's laid out here, I would be equivalent to the rows within this matrix. And of course, that means that the individual values within each of those vectors would be represented by j, and the j would be the columns of this matrix. Now that we know what the rows and the columns are, here, let's put it in the middle here. Let's have a handy-dandy graphic pop up for I and j somewhere, which hopefully you can see now. So now that we know what the rows and the columns are, let's look at this path more closely. And by studying this pattern and how to emulate it, you're going to come to see that it essentially is made up of 4 distinct pathway sections. Here is the first section, where you're starting at, in this case, the top left, and you want to shift right 1 place, and then after that, you want to make a path diagonally down, and you want to keep going in that diagonal down direction until either of 2 things happen. Either you hit this left wall, or you hit the bottom. Either one of those are essentially borders of the matrix. You don't want to go beyond this wall or beyond the bottom of it. Section 2 is going to be what follows immediately after this first section, where you're at the 4 mark. You want to shift vertically down 1, assuming you haven't reached the bottom yet, And then after you do that, and of course record the value, you want to continue diagonally upward. And you want to do that diagonal upward path and record each value you see until, again, one of two things happen. You either hit the top of the matrix or you hit the right wall of the matrix. Then pathway section 3 occurs, where you want to make a shift downward. But unlike in this section, where you also had a shift downward and then went up, in this section here, when you shift down, you want to continue going down in a diagonal direction. And again, you want to do that until you either hit the wall here or you hit the bottom. In this case, you hit the bottom. Finally, the last pathway section that could come up is where you want to shift right 1 and go diagonally up until you hit the borders. In this section here, you also had to shift right by 1, but you went diagonally down here. In this case, you want to shift right and go diagonally up. So those are the 4 distinct pathway sections that we want to emulate in code. And what we want to do to traverse it that way is accomplish the shifting. We want to essentially push back whatever value we see, and then we want to handle the diagonal traversals. But since we don't know how far of a diagonal path we need to trek, we need to use a while loop in order to handle those diagonal traversals. And we need to increment and decrement our coordinates accordingly in order to get the right values on the path. Okay, let's talk about those borders a little bit more. During our diagonal treks, we always want to make sure we don't go beyond the limits of the matrix walls, essentially. Now, the top border and the left wall here can be thought of as the equivalent of whenever I is equal to 0, you're going to be at the top of the matrix. Whenever j is equal to 0, you're going to be bordering the left wall. So those can be used as conditions to make sure we don't go past them during our trek. Now for the bottom of the matrix and the right wall, you can use a similar value here, in that when j is equal to its maximum value here, you're going to be bordering the right wall, and when I is equal to its limit, you're going to be bordering the bottom of it. So when I and j are 0, you're going to be bordering the top and the left wall. When I and j are equal to its limit, you're going to be bordering the bottom and the right wall. So with those pieces of information, what is the general structure of the code going to look like? Well, we need some variables in order to keep track of things that are relevant for us to know. We need to essentially know these limits, what I and what j are, what their max is. We also need to have a new vector of integers to house all of the values in the diagonal order that we want. And of course, we need position coordinates, which aptly can be named I and j. So those are the variables. Next, we would need to handle the edge case of m or n being equal to 1. And in that case, either we return the only vector that's present directly, or we plop all of the individual and only values present in all of the inner vectors into the diagonal order, just one by one, and then return that. Then finally, we're going to have a while loop that is going to run the diagonal path. It's going to consist of if-else statements that is going to represent each of those 4 distinct types of paths that we have. And if none of those options are possible, then we want the while loop to end. And then after that while loop has occurred, we simply return our diagonal order. So with all of that being said, let's get to the coding part. Here are all of the variables that I just talked about. So we have a column size m, we have a row size n, and the column size is equal to the vector at the first I position, i.e. grab that first inner vector that's present, and then tell me how big it is. Subtract 1 from that, and that's the maximum index of the columns. For the rows, we just want to traverse the outer vector and see how many vectors it houses. Get that size, subtract by 1, that's the maximum index we want for the rows. This is the new vector that I've created, just named diagonal order. And then finally, our position coordinates I and j, and they're both set initially to 0. Next up is handling the edge case of m or n being 1. So if the outer vector has a size of only 1, i.e. it only has one inner vector present that houses all of the values, well, that already has all of the values in the order that we want, so let's just return that inner vector. In the other situation, we have a bunch of inner vectors that only have one thing in it, so mat 0, those inner vectors, the size of that is just going to equal 1. And in that case, we want to loop through each of those vectors. So here I'm using a range 4. My type is the vector of integers that I just call the value. And I want to look at each of those vectors that exist in my 2D vector, mat, and then I want to grab my diagonal order vector and push back the value that I want. But because the value is a vector, I need to make sure to list its index as well. In this case, because this vector only houses one thing, the index is always going to be 0. Finally, after that for loop runs, I just want to return diagonal order. Next up, we start the diagonal traversal if the edge cases turn out not to be true. And the very first thing we want to do is add the 0, 0 coordinate value to our diagonal order. So we call pushback and add mat 0, 0 with I and j both being 0. Now we start the while loop, and the condition we want to run is as long as I is less than or equal to its limit, row size n, or j is less than or equal to its limit, column size m. So it's going to run until essentially both have hit their limits. Now comes the code for creating the path sections. The first one we're going to do is the shift right diagonal down section, where we go here and then here. In order to do that, we need to make sure that this condition is true. I is going to have to be equal to 0. So in other words, we're up top here. And we also want j to be less than its limit, column size m. If that's true, then we want to first increment j, so that will handle the shift right by 1. Once we've shifted right, we want to push back the value that we see, so push back mat I, j. Now this while loop is going to handle the diagonal trek, and we want this to run as long as j is higher than 0. In other words, we go as long as we haven't hit this left border. And we want to make sure we also don't hit the bottom of the matrix. So that means that I has to not be equal to the row size limit, n. If those conditions are both true, we're going to want to decrement j and increment I, and then push back the value that we see. So, running back up here, we were at here thanks to the j increment before the while loop. So we want to decrement j, which puts us back here, as well as increment I, which will put us at the position that we want to be. And then we want to make sure to plop that value into diagonal order vector. And you see here in this situation, it's going to stop at this point because at this point we've reached a situation where j has become equal to 0. So we've hit this left wall here and we stop as a result. Next up, second path section here, the shift down diagonal up approach. So if we have a situation where j is 0 and I is less than its limit, in other words, we're somewhere along this left wall here, we want to increment I and then push back that value. So we are here, we want to increment I, so we go down by 1 to get to 7. Now that we pushed back to 7, the while loop here is again going to handle the diagonal up approach. So as long as I is equal to something that's greater than 0, i.e. we haven't hit this top wall here, and we also want to check that we haven't hit the right wall. So j is something other than equal to the column size m. If both of those things are true, decrement I, increment j in order to walk this diagonal path here. Decrementing I, incrementing j puts us at a 5. We still haven't hit either the top or the right wall, so we do it again in this situation. We hit the 3, we record the 3, and in this case we have hit both of these borders, and we stop as a result. Third section comes up, shift down, diagonal down. So we want to make sure if we have j being equal to the column size, so in other words, we're somewhere lined up with this right wall, and yet we haven't yet hit the limit for I, then we want to increment I, add that value, and then use the while loop to do the diagonal approach. So here, we're at the 3. We have hit that limit in this case. We want to go diagonally down, and then use the while loop to get to that 8. The way that's done is as long as j is bigger than 0 and I is not yet equal to its limit, we're going to increment I, decrement j, and then add that value back. So for diagonal down, decrementing j gets us here, incrementing I gets us to the 8. Final section here, shift right, diagonal up, and the relevant conditions here. This time I is equal to its row size, and j is not yet equal to its column size. So we're at the bottom somewhere here, and yet not quite at the right wall. So we haven't yet gotten to the bottom right hand value yet. So we want to increment j, add that to the diagonal order vector, and then if need be, use the while loop to handle the diagonal up. Now in this specific situation here, to get to the 9 from the 8, all we need to do is that single shift by incrementing that j value up. And there is nothing to go diagonally up from, because at this point we've reached these border values. But just in case we hadn't, where as long as I is bigger than 0, as well as j is not yet equal to the column size limit, going diagonally up means decrementing I, incrementing j, and then pushing back that value. Finally, you will notice that with each of these sections here, we're only incrementing and decrementing I and j within these if-else statements. And if none of these are true, i.e. we've run the entire matrix, gotten to the end of the path, if we didn't have this else break condition, the while loop would continue back, loop, see nothing has changed, and because I is less than or equal to row size, j is less than or equal to row size, it's going to loop forever. So to make sure it breaks off as soon as both of those things are equal, we want to simply include an else break. Finally, after this while loop has occurred, and outside of its brackets, we want to return diagonal order, our vector. And with that, the code is complete. This algorithm should work. Fingers crossed. Let's see if that is true, or if I've messed something up. Judging finished. 1, 2, 4, yada yada yada. 1, 2, 4, yada yada yada. These both are the same thing. That's good. Let's do the full shebang here. Pending, judging, and green text. Yay, I didn't mess anything up. Okay. As is tradition, before we hit the button here, let's go through this long amount of code and see what our time and space complexities turn out to be. Well, in terms of our variables and space complexity here, we're having some integers here that represent constant space usage. What isn't constant is this vector here. Now this vector, by housing all of the values that are going to be present in whatever matrix that we're given, its size is essentially going to be equal to m times n. How long the columns are times how long the rows are. Since those are the two variables that dictate how big this vector is going to be, how many values it needs to house, the space complexity of this algorithm is going to be dictated by this vector, and it's going to be a big O of m times n, where m and n are the column size and the row size, respectively. In terms of time complexity here, aside from, say, the edge cases here of essentially being constant and just big O of n here, assuming we're not dealing with those edge cases, we need to look at this big ol' while loop. And we have nested loops present here. But this entire while loop essentially is going to run in conjunction with these inner while loops only as many times as there are values present in the matrix that we're given. So looking up at here, that entire while loop with the nested while loops present is going to run a total of 9 times. The various while loops that we have can range from running a total of 0 times to this is the longest while loop that runs, and it only runs 2 times after we've gotten to this point. For much bigger matrices, the inner while loops are going to run more times, but the maximum amount of operations that this entire section of code is going to run for is going to depend on how big of a matrix that we're given. So in other words, it also depends on m and n. So this code's time complexity should have a big O of n times m, much like the space complexity as well. It's going to be dependent on how big the columns are and how big the rows are, because that's going to dictate how many values are going to be present. And because all of these if statements and the while statements itself are only doing constant work, the time dependency is ultimately dictated by how many times those while loops run. So, space complexity, big O of m times n, time complexity, the same exact thing. And with that, let's look at the rankings here. So, we're right up in the top distribution of time. That's nice. With a very large range, apparently. So, that's interesting. And we are up here in some of the higher level distributions of memory usage. And with all of these high distributions here are in a very small range, so I would expect, say, this to ping pong potentially a little bit, but better than some of the other possibilities here, which range for much larger memory requirements. So, fairly good on the memory usage, fairly good on time usage. Cool! Okay, that was how to solve the diagonal traverse problem on the LeetCode website. I hope this video helped you out in some way. If it did, consider subscribing, since I do these kinds of videos 2 times a week. And as always, I will wish you happy coding and to have a nice day.